Welcome back, everyone. Uh, we have seen so far in this course how to obtain response of a system subject to either well-defined analytical forces like harmonic forces, and we also discussed if there is an arbitrary excitation, how to get the solution. And in the previous lecture, we saw that if the response or if the loading cannot be expressed as a closed form representation like pt equal to some function, then how to employ numerical methods to obtain the solution. Now once we are equipped with this tool, we are in a position to analyze a system or a single degree of freedom system subject to earthquake excitation. And there would we would present a just a we'll discuss in briefly. There is a whole field of earthquake engineering which you may do in an advanced course, but uh, in this basically course of structural dynamics, I'll just giving you introduction, the concept of how to obtain response of single degree of freedom system subject to arbitrary or random excitation like earthquake excitation, and also discuss the concept of peak response and basically response spectra, which is very famously used for analysis and design of a structure subject to earthquake loading. Okay, so let us get started.
Earthquake response of single degree of freedom system, and as we have previously done, we would be focusing on linearly elastic system. Okay, so let me write down the equation of motion that we have been using till now for linear elastic single degree of freedom system. Okay, now finding response to seismic excitation or earthquake excitation is one of the major field where you can see the application of structural dynamics. Okay, and basically the problem becomes in that case, as we have previously discussed. So if I consider this frame representation, okay, of a single degree of freedom system, so let us say initially the system was there and then there was a ground movement. Let us say this is ug of t, and then the relative deformation of a structure, which let us say, okay, so this is the relative deformation u, so that my total deformation is ut of t, which is sum of ugt and then ut. Okay, and this is how it looks like. All right, so basically the problem statement for these cases becomes, okay, in this case pt is effectively represented using mass times ug of t. Okay, so I can substitute it here. All right, so remember that this expression basically comes from assuming that the total acceleration is nothing but relative acceleration of the mass plus the ground acceleration. Okay, and then we substitute in here. Okay, the equation of motion is actually written in terms of total acceleration, however, with relative velocity and displacement equal to 0, considering that there is no external force. Okay, however, when I substitute this expression here, okay, then I can rearrange this and I can get it, okay, get this expression right here. Okay, so again you can write this one in terms of function of t as well. Okay, and this effectively becomes mass times ugt, and this basically is the effective force that we say is acting on this mass here. Okay, in this case. All right, so let us do one more thing. Let us divide this whole equation here by m, so that I can get my expression as c by m, okay, plus k by m u of t, and that is equal to minus ugt, which is the ground acceleration. Okay, This can be further written as, okay, this expression C by M is nothing but 2 zeta omega n times u dot of t, and K by M can be written as omega n square u of t. Okay, this is my expression here. Okay, now these ground motions are basically measured using seismograph. Okay, and we have discussed this, the working principle of a seismograph, in a previous chapter. A seismograph is nothing but in its very elementary form, it's a spring mass damper system. Okay, so it's a single degree of freedom system. Okay, of the spring mass damper elements. Okay, and the way this seismograph actually works is that we utilize frequencies for the seismograph which are quite high, okay, such that, okay, omega by omega n, where omega is the excitation frequency and omega n is the natural frequency of the seismograph. All right, this should be equal to 0.5. Okay, and we introduce very high damping, okay, 60 to 70% in the system. If that happens, then my seismograph can be calibrated to measure various type of ground motion with different frequencies. Okay, so this seismograph actually measure the ground acceleration, which is also many times you would see being referred as strong motion. Okay, we are only concerned about the strong motion because unless the ground acceleration is above a certain threshold, okay, it is not going to do any damage to a structure. So if you consider magnitude of earthquake, let us say less than 4, typically it does not lead to any kind of damage in the structure. Okay, so in terms of strong motion, what we do, these seismographs are actually located at various distances from the source of an earthquake. Okay, and these seismographs are lying there for a long period of time, 20 years, 30 years, like that. Okay, and you can imagine these earthquakes need not to be very frequent. Okay, it might come once in a lifetime, let us say once in a 50 year or 100 year. Okay, and the idea is that you cannot continuously be measuring the acceleration due to very small earthquakes like less than 4. Okay, so these accelerographs are actually triggered when the acceleration is above a certain threshold, or when it is calibrated to, okay, be triggered with some other mechanism. So what do we do? These accelerographs would give you strong motion, and then it would also report you the strong motion duration of an earthquake ground shaking. Again, it is based on the same principle that you are only bothered about the ground motions, okay, which are going to have any realistic effect on the structure. So strong duration, there are different way to characterize the duration of a ground strong of a strong motion. Okay, there is areas intensity, there is, like, threshold, the max with respect to maximum pg or certain kind of thing. But basically, just remember that these do not continuously measure, but it measures above a certain threshold. Okay, and each of these, okay, each of these accelerographs, which are located at different location, they can measure depending upon what kind of accelegraph are they, in one direction, two direction, or three direction. Okay, so, okay, two horizontal direction and one vertical direction. Okay, so typically any earthquake would have three components, although some of the old accelegraph would give you used to give only two components. Okay, so usually any earthquake would have three components. Of course, there are additional research which are now characterizes six components of the earthquake, including rotational. Okay, but we are not bothered about that. Okay, this is beyond the scope of this course. So remember that accelegraph would provide you basically the acceleration history which would be in terms of, okay, either time acceleration, okay, so time and then acceleration, which might be expressed, let us say, in terms of units g. Okay, so something like, let us say, like that. If it is an interval of, let us say, 0.02 second uniform interval, okay, it would be something like this. Okay, so this is just the fictitious value. So it would give you basically discretized value of the acceleration at different time instance. Okay, now in the previous chapter we have seen that given any arbitrary excitation, how to find out the response of a system, okay, to any arbitrary excitation pt. And what do? Basically we use numerical methods. Okay, so depending upon whether the system is linear or non-linear, okay, we basically discussed three methods. One was interpolation, excitation interpolation method. Okay, other one was central difference method, and we also discussed Newmark's methods. Okay, so any of these methods can be utilized to get the response of the single degree of freedom system subject to this ground excitation. Okay, now depending upon, okay, depending upon what is the structure, there could be different response quantities of interest. All right, so for example, it could be of absolute values of the response quantity, like u dot of t, the total acceleration in the system. Okay, or it could perhaps be total velocity, let us say, or total displacement. Okay, or it could be relative acceleration, relative velocity. Okay, note here. Okay, relative velocity and relative displacement. Now, usually what happens for a structural engineer, okay, the total velocity is not of concern to us. Okay, what is concerned to us is basically the total acceleration. Okay, and I will talk about where do we actually utilize that. Okay, but also total displacement is also concerned to us. Okay, and of course the relative displacement, which is basically the most important parameter. Okay, if you want to analyze a structure, okay, to find out the internal forces in the system. Okay, now the idea is, how do we apply the knowledge of structural dynamics to earthquake engineering? Okay, so let us say somehow I'm able to find out these response quantities. Okay, once these response quantities are found out, okay, then we can utilize this to get the forces and moments in a structural member. Because in the end, remember, as a structural engineer, your goal is to find out basically forces on a beam or a column. Okay, so depending upon, let us say this is axial load, this is shear force, and this is M. Because once you have these forces in the members, you can perhaps go ahead and design the structural member for those forces. Okay, so utilizing the knowledge of a structural dynamics, we are going to find out the values of these parameters. Okay, and then from that we are going to find out the internal forces. Now, if you remember, the internal force in any structure, okay, it depends only on relative deformation. Okay, it only depends on relative deformation. It does not depend on velocity, or it does not depend on the acceleration. Okay, it only depends on the relative deformation. So if we somehow able to find out this parameter ut using some sort of numerical methods or any other method, then I would be able to find out the forces in the member. And one of the simplest example would be, let us say I have a cantilever column here. Okay, and under the action of, let us say, UGT, okay, it has certain deformation, of course. It will be some value like this, but let us say relative deformation is U of t. Now you know that if the deformation of U of t the force, let us say V here, would be nothing but, okay, I can write it as 3 EI by L cube times U of t. Okay, so if you know the displacement, okay, knowing the structural property and geometric and material properties of the structural member, you can find out or relate it to the forces in the member, and then you can design the member to sustain those forces. Okay, so that is what we are going to learn in this chapter. Okay, so let us see how do we do that. Now I have already written down an alternative form of the equation of motion. Okay, so we said that our equation of motion can be written as, okay, like this, plus omega n square ut equal to negative of ground acceleration. Now, if you look at carefully at this equation, can I say my displacement u depends only on two factors here? Which are those factors? Parameters, basically zeta and omega n. Because if there are no, I mean, there, if you look at this equation, there, except these two parameters, there are no other parameters, okay, involved in this equation. So basically u, or the displacement, depends only on omega n, or you can also call this like tn, basically the time period and the damping in the system, only these two parameters. All right, so I can write down my ut as a function of course the time t, okay, and then the time period of the system and zeta, okay, which is the damping in the system. All right, and similarly the acceleration, okay, which is related to u, and velocity also depends on only these three parameters. So given any ground motion, okay, given any ground motion ug of t, all right, my response ut only depends on the time period and damping in the system. Okay, and for this case, remember, it does not matter whether the system is heavy or lighter, or whether it is flexible or rigid. Okay, two different systems with different masses and stiffness would have similar displacement if the ratio are such that it gives you the same value of the time period Tn. Okay, so that you have to keep in mind. Okay, so depending upon these two parameters Tn, okay, the response to a ground motion might differ. Okay, so basically if you consider, let me consider first two cases, or like two series of cases here. Okay, so in the first case, I'm going to consider systems in which the time period is actually varying but the damping is same. Okay, and in the second case, I'm going to consider systems in which time period is same but damping is actually varying. All right, so let us see what happens. So for any, and I'm just drawing like an approximate representation. So for any ground motion ug of t, all right, so for any ground motion ug of t, okay, let us say the first system is tn is equal to 0.5 second, zeta is equal to 2%. Second one is tn is equal to 1 second, zeta is equal to again 2%. Okay, and third one is tn is equal to 2 second and zeta is equal to 2%. Okay, now in the second case, let us say tn is same at 2 second. However, zeta is first is equal to 0. In the second case, again tn is same but zeta is 2%. Okay, and in the third case, let us say tn is again, I mean it's same, but let us say zeta is equal to 5%. Okay, so what happens, okay, typically if you given a ground motion, okay, this would look like something like this. Okay, All right. As you increase the time period, okay, typically it would look like something like this. Now, if you further increase the time period, it would look like something like this. Okay. And this is the direct consequence of increasing the time period, which is evident from the response. If you consider the response here, okay, first the amplitude is smaller, and the second, basically, the time period of the response is smaller. Okay, but as you go to 1 second and 2 second, you can see that the time period of the response is also increasing, as well as the amplitude is also increasing. Okay, now let us go to the second case in which it is somewhat similar to this case. Okay, so let me just draw it like this. Okay, as I increase the damping, so this was with the zero damping. As I increase the damping, what you will see, okay, while the this remains same, but the amplitude actually decreases. Okay, and with the further increase in damping, this further decreases. Okay, all right, so these are the typical characteristic. Okay, and you can go ahead and perhaps obtain the response of any single degree of freedom system subject to a selected ground motion with different time period and damping, and these type of characteristics would be obtained. All right, so two things are to be noted here. First, that the response of a ground motion or response of a linear elastic single degree of freedom system can be completely characterized using the time period of that structure and the damping of the structure. Okay, so this you have to keep in mind. Now, let us come to the response quantities that are of interest to us. Okay, so we want to look at response quantities that are of interest to us, and we said that it is the relative displacement, okay, or it could be total displacement and the total acceleration. Now, relative displacement, as I have previously mentioned, leads to the internal stresses, or basically forces and internal stresses in the structural in a structural member of a structure. Okay, then the total displacement might be important for cases where you have buildings that are adjacent to each other. Okay, so that you need to find out what is the separation between these buildings that need to be provided, so there is no pounding damage. Because what happens when you have structures of different time period shaking with respect to shaking due to the ground excitation, okay, at this point, due to the displacement of the structure at the top of it, this structure might go ahead and basically impact this structure at the point of contact. It might lead to the damage to the structure. So here the relative displacement is not the important factor, but for pounding you need to find out what is the effect of the ground displacement plus the relative displacement, because that is what would be the responsible displacement here that might lead to, okay, making decision regarding the separation of this building. Okay, similarly for this one it would be UGT plus U of t. Okay, so let us say this is U1 of t and U2 of t. So you need to find out the total, basically, displacement here in this case if you want to assess the pounding damage. So relative displacement is important in cases where you want to find out internal forces and stresses. Total displacement becomes important if you have to consider the pounding damage. Okay, and total acceleration becomes important if you have some sensitive equipment. Okay, sensitive equipment inside a structure. Okay, so whether if there is sensitivity, whether it is kept on floor or whether it is connected to the ceiling, these equipments are actually sensitive to the acceleration or the total acceleration. So there it becomes important. Okay. So, and of course, like, apart from that, the forces in the members, okay, which of course is related to the relative deformation. So basically, these are the typical response quantities that are of interest to us. Okay, so the question becomes, I have this equation of motion, let us say, okay, how do I go from this equation of motion to the forces, finding out the internal forces in the structure? Okay, and what we are going to do here is basically introduce the concept of equivalent static force. Okay, let us see what is an equivalent static force. Now, as I've told you, there is internal forces or stresses in the structure depends only on the displacement, okay, not on the acceleration. So let us say I am able to solve this equation and find out the value of u of t, okay, with any method, any numerical method. Let us say this is my structure and I'm able to find out the value of u of t. Okay, once that is found out, the internal forces in the structure can be determined by considering the response of this, let us say, single degree of freedom system subject to an equivalent static force which is equal to the lateral stiffness k of the systems times u of t. Okay, if you apply this load, okay, and find out subject to this load, of course it would be a static analysis, that's why it's called equivalent static analysis, that you first do the dynamic analysis and then you find out at each whatever time instant of interest to you is, you find out what is the displacement, okay, or at every time step you find out the ut value, okay, and then the response to a system can be found out considering the force under a action of a statically applied force which is equal to k times ut, okay, and you apply that, what you would find out, the response in the structure is similar if you had considered the dynamic analysis and found out the same thing, okay, and this can be observed from the equation of motion like this. If you consider that in terms of the value total value of the absolute value of the acceleration, okay, remember we had this equation here, plus ku of t. Okay, so somebody might ask a question, why is this external force is k times ut and not m times ut double dot? Because in the end the external force is basically the total acceleration that the structure is experiencing, right? Mass times the total acceleration. So why not this force? Now if you consider this equation of motion here, okay, that question can be rephrased if I write it like this, okay, mut is equal to minus c ut and minus ku of t. Okay, so the question becomes, why I am neglecting this? Because if I'm considering KUT, it is effectively that I'm considering the mass times total acceleration if I neglect this damping term here. Okay. Now, the reason that I'm considering only KUT as an equivalent static force is because any type of damping mechanism, let us say it is due to viscous damping mechanism, if I'm assuming the nature of the energy dissipation to be viscous damping. Okay, so if there is some energy dissipation at the joints or any other mechanism, those kind of forces actually do not lead to any kind of internal stresses in the member, mostly, but I mean there are, like, if you go into nonlinear analysis, of course nonlinear systems are equated as equivalent linear system, and in that case the damping becomes important. However, for this case, for equivalent static analysis, we can say that the response ut, okay, if I apply this force ku of t, okay, how much would be the response in the system? Let us find that out. Okay, I have done the dynamic analysis, okay, using this equation, these equations. So basically I've solved this and found out the ut in the system. Now let us say if I apply the fst equal to ku of t, how much is the displacement in the system? Okay, and this is a static analysis. So for this case, can I say that if I apply this force, the displacement in the system, this displacement here would be the lateral stiffness of the system, total force divided by the lateral stiffness of the system, which is u of t. Okay, so whether I do the dynamic analysis and find out ut in the system, or I apply a static equivalent static force of kut and find out the response in the system, the response in terms of deformation would still be u of t. Okay, so that's why we consider a equivalent static force. Okay, and this is very central. This concept of equivalent static force is central to earthquake resistant design. Okay, and it is basically adopted in many of the design codes, earthquake design codes around the world. Okay, all right, so I hope that concept is clear to you. Okay, so let us see, once I have the ku of t, what would be the base shear in this structure? Okay, so base shear, if I consider due to this applied force ku of t, and now remember that once I find out ut, okay, I apply the equivalent static force ku of t, then I'm doing basically static analysis. So I'm interested in finding out what is the base shear and basically what is the base moment, because once these quantities are known, then I can distribute the total base shear, okay, in the structure or the moment, and the structure can be designed for that. Okay, so base shear in this case, if you consider the free body diagram subject to this equivalent static force, can I say my base shear would be nothing but whatever the equivalent static force is, and that is equal to ku of t, and my moment would be nothing but whatever the fst is times the height of the structure, okay, which I can also write as base shear times the height of the structure. So let me write it again. Okay, let me write this equation for the base shear and moment again. Okay, and then see what do we get. Okay, so basically saying subject to equivalent static force of ku of t, okay, I am finding out my base shear as, okay, my base shear as same as fst, okay, which is equal to ku of t. Now one more thing can be done here. If you look at this expression here, k can be written as m omega n square. Okay, remember k is nothing but m omega n square, so I can substitute it here and write it as m omega n square u of t. Okay, now if you consider this expression here, m omega n square u of t, this quantity here has units of acceleration, and basically we write this expression as m a times t, where at is referred to as pseudo acceleration. Okay, so it is referred to as pseudo acceleration. All right, now this acceleration is actually not the actual acceleration of the system. It has units of the acceleration, but remember the actual acceleration of the system is ut of t, and this at is not equal to ut of t. Okay, and that is evident from this equation here, the equation that we have been considering. Okay, so if I write down in terms of total acceleration, remember my equation of motion becomes this plus omega n square u of t. Okay, and my total acceleration is actually minus omega n square u of t, which is actually the a of t here. Okay, minus 2 zeta omega n u of t. Okay, so I have this term here which differentiates the total acceleration from the pseudo acceleration here. Okay, and if a system has zero damping or when the velocity is zero, so when this is zero or when the velocity is zero, then of course my total acceleration, okay, or the absolute acceleration is the pseudo acceleration, but in general that is not the case. So you have to keep in mind that distinction. Okay, all right. If that is the case, then I can say I can either apply k times ut as equivalent static force, or I can also apply mass times acceleration, the pseudo acceleration, where at is basically omega n square u of t. Okay, now if that is known, okay, then my base shear can be again written as vb of t is equal to equivalent static force. This can be written as either ku of t or ma of t. Okay, and my base shear is fs of t times h, or I can also write as vb of t times h. Okay, now remember what I have done here. Okay, for this single degree of freedom system, okay, I found out at any time instant what is the ut, then I applied the equivalent force fst equal to k of ut or m of at, and subject to this force I found out what are the internal forces. For example, in this case, the total base shear and the total base moment. Okay, so from the dynamic analysis, okay, for this seismic excitation, I found out what is the base shear and moment, and once that is known, I can go ahead and do the seismic resistant design or earthquake resistance design. Okay, earthquake resistant design of these structural members. All right. Okay, once that is known, okay, it becomes typically for a designer, it becomes very difficult. And remember, here we are only considering single degree of freedom system, but in reality, any structure is multiple degree of freedom system. Okay, and I mean, it is computationally expensive to do response or to numerically analyze the system and find out the response at each and every time step. Okay, so what do we do? And also that if a structure is experiencing several magnitudes of forces, typically we design a structural member for peak forces. Okay, so if somehow I can find out the peak values of the response quantities, okay, I don't have to go ahead and do the numerical analysis every time. Okay, and I have told you previously that if a ground motion is there, okay, then the response of a system to this ground motion depends only on these two parameters Tn and zeta. Okay, so what we are going to do now, we are going to introduce concept of response spectrum and then see how this concept of response spectrum can be utilized, okay, to come up with a method to efficiently find out the response of any structure. Okay, so response spectrum is nothing but peak response, and this definition is basically we are defining with respect to seismic excitation. So peak response of a single degree of freedom system. Okay, all right, so this is the peak response of single degree of freedom system, and of course we are considering linear elastic here. Okay, because there are also non-linear response spectrum, but we are only considering linear response spectrum. Okay, so this is a peak response of single degree of freedom system. I should not say A. Okay, all, let us say, peak response of all single degree of freedom system for a particular ground motion. Is for a particular ground motion. And let us see how is that useful. So let's say that peak response could be anything. It could be displacement, it could be velocity, okay, or it could be, let us say, acceleration. Okay. Now let us say if I have, okay, a plot of peak response, let us say this is u naught, okay, with some arbitrary function. I don't know what that is. I don't know the nature of it. Let us say it's any arbitrary, okay, function, and let us say this is Tn here. Okay, all single degree of freedom system means that systems with different values of Tn here. Okay, so basically what do we do? Okay, if you go back to the graph that we had considered here, okay, this one, just go ahead. Yeah. So remember, depending upon the value of Tn, it's 0.5 or 1 second or 2 second. I basically got different value of the peak response, isn't it? Okay. And similarly, different value of damping also give me different value of peak response. So now let us consider a single value of damping and different value of time period. I can perhaps plot the peak responses on this system here for all possible values of Tn. Okay. And this is specific for a ground motion. So each ground motion will have a response spectrum. Okay. So each ground motion would have a response spectrum for particular value of zeta. Okay, let us say it is 5%. Now, if that is derived and I am designing a certain system for which let us say Tn is, let us say 0.75 second. Okay, then I can come here. Okay, I can come here and I can find out subject to 0.75 second what is the response of this system. So what is the value of u naught? Okay, so I would be basically finding out what is the value of u naught or the peak displacement. Once the peak displacement is known, I can again basically adopt the same procedure where I'm going to apply the peak value of the equivalent static force, which is k times u naught, or m times, let us say, peak value of pseudo force, which is m times a. Okay, and subject to this force, I can find out what is the base shear and what is the base moment. Okay, so if the peak values are known, that is what our goal is. Okay, for design of any structural member. So this is how we connect the idea of structural dynamics using response spectrum to design a system for any seismic excitation using the peak responses. Okay, so we are considering, remember, we are considering peak responses. So I can write down, okay, that my peak response for any system, okay, so peak response in time u naught, Tn and zeta would be basically, I would find out what is the maximum response of this quantity here is, okay, so this is for a particular Tn. Similarly, I'm going to find out the velocity, okay, and again the maximum over Tn and zeta, and then total acceleration here, okay, again this is this, okay, so this would be Tn and zeta. All right, so using this we can vary the value of Tn, okay, and we can find out different response spectrum. For example, this would give me, okay, this would give me, if I do for displacement, a deformation response spectrum, okay, deformation response spectrum. Okay, this would give me velocity response spectrum. Okay, and the third one would give me acceleration response spectrum. All right. So these three response spectrum are of interest to us. Okay, and given these three response spectrum, I can go ahead and I can find out the response. Now let us see. Okay, for any ground motion, let us say if I have a ground motion which has a very random response, something like this. Okay, now depending upon the okay, value of the time period of the structure as I have shown you before. Okay, so let us say this is time period 0.5 second. Okay, let us say this is time period, okay, 1 second, so that it is little bit spaced apart than the above, and the amplitude is also more. And then I have the third one. Okay, which is tn equal to 1 second. Now each of these would give me certain peak responses. Okay, let us say this is u10, let us say this is u20, and let us say this is u30. Okay, so I can, if I plot this, the displacement response spectrum, what will happen? Okay, if this is my displacement u0 and this is time period, these would correspond to tn. Remember, this is 0.5 second here, and this is u10 value. Then this would correspond to 1 second. Okay, and let us say this is 1 here, not actually, this is 1 second, and this is 2 seconds here. Okay, and this is actually 2 second, and each of these correspond to peak responses that we have obtained. Okay, u20 and u30. So this is how the displacement response look like. Okay, and similarly we can go ahead and we can find out the basically the velocity response spectrum and the acceleration response spectrum. However, if you remember, when I wrote down the equivalent static force, okay, is actually k times the relative velocity, which is equal to mass times pseudo acceleration here. This is not the total acceleration which I have written here. Okay, so it would be useful for me, okay, if I can get the response spectrum for pseudo acceleration. Okay, so if I can somehow get the response spectrum for AT, and remember AT is related to UT by how? Omega n squared times UT. So if I can get the value of U0, let us say now I'm start to represent this as D, okay, the peak value as D, okay, I can find out the peak value of the pseudo acceleration as multiplying this with omega n squared times t, which I can also write it as 2 pi by tn times t. So if my displacement response is obtained, okay, then I can go ahead and I can obtain the acceleration response. Similarly, I can also define a new parameter called pseudo velocity. Okay, I can define pseudo velocity as v equal to omega times ut. Okay, remember there is only single power omega n times ut. Now this is vt here. Now if you look at it, this quantity here has units of velocity. However, my vt is not actually the relative velocity in the system. Okay, so do not again get confused. So that's why again I refer to this as pseudo velocity and not the absolute or the relative velocity. Okay, so I can also define pseudo velocity Okay, so I can get the pseudo velocity spectrum as well. So instead of finding out velocity response spectrum and acceleration response spectrum, I am more interested in finding out the pseudo acceleration response spectrum. Okay, because my equivalent static force is actually a function of pseudo acceleration, not the absolute acceleration. And if the equivalent static force is a function of pseudo acceleration, then of course my base shear and moment would also be a function of that. And because of this relationship, okay, I can write down the relationship between basically A by omega n is equal to V times omega n d. Okay, and this describes the relationship between relative displacement. Remember, displacement is relative. Okay, it is not pseudo, it is the actual relative displacement in the system. And velocity is pseudo velocity and acceleration is pseudo acceleration. These are related by these expressions here. Okay, now as I've previously told you, okay, that for any system, the pseudo acceleration is actually not equal to the total acceleration in the system. Okay, so the peak value is also not equal to the peak value of the acceleration, okay, in the system. Okay, however, if zeta is very small, okay, let us say 2%, 1%, or 5%, okay, these values are quite close actually. Okay, and we can go ahead and plot this, okay, for different value of damping, okay, at different for different value of Tn as well. Okay, for all realistic purposes, these are quite close. Okay, all right. So now I know that if I know one of either A, V, or D, I can find out the other two. Okay, because these are okay related by this expression here. Okay, all right. Now knowing that, okay, that I have acceleration response spectrum, which typically something looks like this. So let us say this is D here and this is Tn. Okay, I can also plot the velocity, pseudo velocity response spectrum, which would okay look like something like this, and then acceleration, pseudo acceleration spectrum, which looks like this. So this is V and this is A. The horizontal axis is Tn. Okay, once one of these are obtained, then it becomes very easy for me to find out the peak response in the system, isn't it? So look at if I look at this here, okay, remember the peak response is basically would be obtained subject to the equivalent static force, okay, which is either k times u naught, or let us write this k times d, or I can also write this as mass times pseudo acceleration. So either k times d or mass times pseudo acceleration. Subject to that, I can find out the peak value of the base shear, which is FSO times the height of this structure, okay, and mass as whatever the base shear times the height of the structure. Okay, there is no height here. This is simply base shear is the applied equivalent static force. Okay, and we utilize this knowledge. Now if you look at the expression for the base shear here, okay, basically we get as mass times the peak acceleration, and if I write down mass as weight divided by g, okay, this can also be written down as a divided by g. Now this quantity here, which is the peak pseudo acceleration divided by g, okay, times the weight of the structure, okay, this is also many times referred as seismic coefficient. Okay, seismic coefficient. Okay, so The initial seismic resistant design of the structure, when the practice of earthquake engineering was not yet matured, had not matured, at that time, what people simply used to do, remember, initially all the structure were used to design for vertical loads. Okay. And earthquake is actually a lateral load. Okay. So everybody knew that you have to design the structure for lateral loads to sustain earthquakes, but nobody knew how much. So basically, initially, they started the design as such that they are going to take percentage, certain percentage of the seismic weight, let us say 10%, and apply it laterally and design the structure for that. And even to this date, that method is reasonably accurate. Even if you design a structure for, let us say, 10% or 20%, even if you do sophisticated seismic analysis, your basically results come out to be somewhat closer. Okay. All right. Now let us get into finding out the peak responses. Okay, back to peak responses, and we have already discussed that if somehow I can get my u naught or d, or let us say pseudo acceleration, or let us say even v, then I can go ahead and do the equivalent static analysis. Okay, so let us say this is fso is equal to k times u naught or k times d, or also equal to mass times acceleration. The total base shear would be, as I've previously indicated, fso naught equal to k u naught times acceleration. Okay, and basically the moment, the base moment would be fso times h. Okay, and we would be following this procedure, and depending upon what response is spectrum is available to you, you can directly get d, or even if a is given, let us say the pseudo acceleration is given, or v is given, you can find out the other parameter. Okay, all right. Okay, now let us get on to, now we know how to find out the peak responses. There is one challenge here. Okay, challenge is, I have shown you that an acceleration response, pseudo acceleration response spectrum looks like this. Okay, so there are a lot of non-uniformity. If you look at it, a lot of jagged lines. Okay, this is still like very smooth, but actual response spectrum would look like something like this. Okay, now if you measure, okay, if you measure the acceleration at the same site after certain number of years, the same thing would now look like this. Okay, and again after certain year it would again change. Okay, so the question becomes, if I have to design the structure, so basically to design the structure I need to find out these peak forces and peak moments. Okay, which one to choose? Okay, remember I've told you this is at the same site, only that it is measured at different instances of time. Okay, and the response spectra would be quite different, in terms of the peaks that you see here. Okay, so the question becomes, which response spectra should I use? Okay, so actually what happens in these cases, that just for a, if you select any response spectra, just for a small change in the time period, your forces would increase substantially. Okay, and that is not realistic, from the design perspective. So what do we basically do? We define or we develop something called design spectra from a set, or let us say an ensemble of, okay ensemble of several response spectra. And how do we do that? Remember, if you take the average of these response spectra here, how would they look like? If you look at this, the average would look like, okay, little bit smoother compared to individual response spectra. Okay, so this, let us say this is the mean value of different response spectra at the same site. Okay, now typically what do we design? There are different, like, very sophisticated design procedures. Okay, where you do seismic hazard analysis, do a statistical analysis to come up with. But in very simple or layman term, if we consider, okay, let us say mean plus standard deviation, it would look like something like this. Okay, so that it would consider, okay, most of these peaks, okay, to be captured under mean plus standard deviation. Okay, and then approximate that with set of straight lines or curves. Okay, so that my response or my design spectra in reality looks like a much smoother curve, which is the idealization of the, or which is the idealization derived from the statistical analysis of several response spectra. So this is my design spectra, and this is what we use in design of structure, not a single ground motion like this. Okay, so design spectra basically obtained doing statistical analysis of several ground motions or several response spectra. Okay, and then come up with some conservative estimate of the acceleration at different time period, and then approximate that using, okay, curved lines or smoother straight lines. Okay, so these lines basically would represent the response spectra at the site. Okay, and this is what is utilized in the design of the structure. Okay, all right, so these are basically the concepts, okay, that are required to understand. Once you know what is the value, okay, so from here, let us say this is the pseudo acceleration response spectra. Okay, from here, for a given structure or for a given value of Tn, you can get what is the value of the peak acceleration. Once you know the peak acceleration from here, okay, you can go ahead and you can find out the equivalent static force that you need to apply on this structure. Okay, and subject to that, okay, or you can also write it as kd, where d is basically, a by omega n square. Okay, you can find out the peak base shear and peak moment. Okay, and this is the typically the procedure that we use. So this is a very simplified presentation of the concept of earthquake resistance analysis and design using response spectra. Of course, there are, like, a much more detailed discussion of this in that would be presented in an earthquake engineering course, but for this case, this is how we relate or apply the concept of structural dynamics to earthquake resistance analysis and design of structure. All right, okay, with this I would like to conclude this lecture. Thank you.